Welcome back, everyone. So for the main seminar, we have our speaker, Jennifer P. from the University of Oxford, who will be talking about game-theoretic classification for C-star algebras. Take it away.
Thanks. Thanks for having me. So I will be talking about a classification program for C-star algebras, which I know that not everyone is familiar with, and I assume that for most people here, the briefer on games and logic is also new. So the board will help slow me down a little bit, but I do have a bad habit of trying to go way too fast when I'm giving a talk. So please stop me at any time. And just before I get started with the things that I had planned to speak about, for how many of us is it still kind of like feeling a little nebulous and unclear, this relationship between games and logic? Ish. Okay, so I'm going to really briefly, probably Mira intended to get to this during her talk, but such is the nature of a 30-minute talk, it's very hard to say the things you want to say. So let me give a couple of examples, the same ones that she gave, for this correspondence between games and these sentences. So this first example that she gave was you have some structure A which is finite, and some other structure B whose cardinality is infinite. And then she made the point that, well, you can tell this equivalence, like 2 has a duplicator, has a winning strategy for this game, only when, I shouldn't use n for this then, finite, only when n is at most the cardinality of A. But how should you think of this? Really, the thing that distinguishes A from B is that there's this sentence you could write, just like the existence of x1, x2, blah, 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 xn minus 1, so that they're all not equal, right? So like x1 not equal to x2, and x2 not equal to x3, and blah, 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 you get the point, right? There's some finite sentence I can say here which says there exists n plus 1 many elements, and B says, yes, this is true, and A says, no, that it's not. And this point about quantifier rank is that really I have n plus 1 quantifiers here. I'm saying there exists an x1 and there exists an x2 and a blah, blah, blah. So the point is somehow that at the n plus first stage, A and B are told apart by this sentence. So this is the point about games and logic actually being concretely the same in this picture. And you can do the same thing with many of the examples that she gave. So maybe 2, this example where A is the natural numbers with their usual ordering, and B is the integers with their usual ordering. And the point is, the distinguishing sentence is somehow there exists some x, so that for all y, y is not less than x, something like this, the existence of a smallest element. A says this is true, B says that it's not, and then these two things, it was determined, they're one equivalent, but they're not 2 equivalent. And the point is you can write down something with exactly 2 quantifiers, which tells them apart. So this is, and then, okay, this extends for the countable ordinal case. And you can look at this for isomorphism. But hopefully, just in terms of the way you internally feel, this helps a little bit with saying games and logic are equivalent. Okay, so I'm going to talk about structures way more complicated than sets with ordering. And in particular, the objects of C-star algebras are not going to be discrete. And there's some analog of these discrete games established for the continuous setting. And I won't really get into the specifics of that because I don't think it's that important. I mean, you're all analysts. You can kind of see that, I'll bring it up after I state the main theorem. I'll make some point about this. You can see that there's some modification of this game where instead of like sentences being exactly true, you want to like satisfy some properties up to epsilon and then yada, yada, yada. If for all epsilon the things hold, then you win the game. Okay, great. Let's talk about C-star algebras. So I don't know how how many talks everyone here has already seen about C-star algebras? Do we all know what a C-star algebra is? Yeah, okay, great, cool. So we can do logic with C-star algebras. So now instead of this language just being a relational thing, you have some language for C-star algebras. And what should this include? Okay, well, you should have some symbol for the zero element, some symbol for the unit. I'm going to deal with unital C-star algebras. And then some symbol for scalar multiplication by elements in the complex numbers. Something for addition of algebra elements, multiplication of algebra elements, the adjoint, and a norm. Okay. So much bigger language, not just binary relations. I've got some unary relations, some binary relations, and then this thing which is some real valued predicate instead of something that takes values true, false. Okay, but there is a logic that you can do for C-star algebras. What's some notable things? You should be thinking about replacing, so formulas are going to be the same in the sense that you can make some finite statements with ands and ors and some quantification. But quantification you should be thinking of for all as a supremum and existence as an infimum. So, for example, a C-star algebra is commutative if it satisfies, so the C-star algebra is called A satisfies that the sup over all x, sup over all y, norm of xy minus yx is 0. Why is 0 the right notion of truth? Well, if I'm in some metric structure, how do you tell when two things are equal? It's when the distance from each other is 0. So in the continuous setting, you should be thinking about 0 as the truth value, and then you can replace your quantification by suprema and infima. And then you can develop logic much as in the discrete case. There's a notion of these games, and just like in the discrete case, a form of Scott's isomorphism theorem holds. So for every A and B, there exists some countable ordinal. Well, for every pair of separable A and B, there exists some countable ordinal alpha, so that agreement up to alpha in these games determines isomorphism. Okay, great. So that's what I want to say about C-star algebras. What about their classification? How much have we heard about classification of C-star algebras? Some, here and there. All right, cool. So maybe I'll say some things that you've already heard, in which case I apologize. Sorry. But so there's this big program where you want to determine C-star algebras up to isomorphism. And of course, you want to do this using some invariant, which is simpler than the C-star algebra. And some initial results in this vein. So early classification. And this is George Eliot, 76. So for approximately finite dimensional C-star algebras, A and B, A and B are determined up to isomorphism by, okay, they're ordered K-naught. Okay, and if you don't know what ordered K-naught is, this is fine. It's just some group that you can form out of taking a generalized notion of projections and keeping track of where, I should also say unital. All C-star algebras in my talk are unital, except for the ones that definitely shouldn't be, like the compacts. Okay, all right, so we have this early classification result which says for some C-star algebras, I can determine this via some isomorphism on groups. And there's some claim that, groups with an ordering should be considered simpler than all this information encoded in some C-star algebra. So good, I have something nice and computable. How is this related to the thread of what I'll be talking about today? There's the following theorem. This is this will come back in a second, by 4 authors, Devant, Vaccaro, Ignati, Velikovic. And this is 2012 or something like that. 22. All right. So much later, there's this observation kind of that when you're playing these games, what are you really doing? It's like you're building partial maps. So in the first step, you're saying, oh, I send this element A to this other element B, and then I want to extend in a way that builds towards an isomorphism. And this observation really tells you that there should be something said about this classification in terms of these games. So their theorem is for this class of algebras, for AF algebras, AB, if the ordered K naught of A is whatever, alpha equivalent to the ordered K naught of B, then, oh, I should write this, omega times alpha, then A is alpha equivalent to B. All right, so in terms of these games, what I'm saying is I can play the game on the groups, on the discrete structures. At the cost of going countably many more steps each round, I can build this, alpha level partial map, partial isomorphism between A and B. Let me, I know it's like hard to see, but also I want to take back the board later. Okay, great. How do they prove this? They really kind of walk through the argument that Elliott gives in 1976, plus, okay, a lot of cleaning up that happened in the 40 or so years that followed. So they walk through this intertwining argument, and they literally just transfer the game. So they're saying, like, oh, you have some nice winning strategy on the level of K naughts, and at the cost of countably many steps in this intertwining argument, you can build the map on the C-star algebras. Okay, if that made no sense to you, don't worry about it. Point is, you do some bootstrapping of the C-star algebraic argument to obtain this. Other point is that this begs a really natural question. So Q, what about the rest of classifiable C-star algebras? So probably you're all at least vaguely familiar that since 1976 there's been a ton of work doing this classification for C-star algebras, and there's a much larger class than just approximately finite dimensional things, and we have a good underlying invariant for this class.
Also, is there just the one-way implication? Like one-way?
Yeah. This is a good question. Okay, so the question was, here they just have the one-way implication. Somehow, in the C-star algebraic case, it's clear that if A and B are isomorphic, then their K-theory will be isomorphic. You just compute it from that. To do the converse, so continuation of this theorem, continued. They get a partial converse, which is that if A is, I think it's omega plus 2, whatever, it doesn't matter, something, times alpha equivalent to B, then, here's the big thing. I have to stabilize. Then K naught of A, alpha equivalent to K naught of B. Yeah, somehow the direction that should be easy is hard. And the direction that should be, I mean, this one, it's like you already have the blueprint of a proof, which is made by extending a map one step at a time. So it just like fits very nicely into this framework. And in the opposite direction, you're like, well, I have to compute K-theory, which means I have to take matrix amplifications, and then, I don't know. You don't get a nice full converse. So, okay, you can also add this to this question. Now I need you to swear that I didn't plant you in the audience to ask this, because it will make my theorem actually a little bit better. Okay, so Basically, the thought was, okay, yes, you can probably repeat exactly this argument and go through lots and lots of complicated C-star algebraic machinery to get the analogous theorem coming from logic, but it's a pain, and nobody wants to do it. And kind of the point of my talk is we can get this, and not only do we get it, the proof is nice and interesting and leads to some cute things about the UCT. All right, so let me first, well, should I state the class? Yeah, sure. First, let me state pseudo-state the classification theorem for C-star algebras. I won't actually, it's not important to me what most of the assumptions are, so I won't actually write them. So there is a very nice class of C-star algebras such that for A, B in this class, A is isomorphic to B if and only if this invariant called KTU. Okay. All right. Couple of things. I will want to focus on some of these assumptions later, but most of them I don't care that much about. If you've seen talks about this before, then you've heard unital, simple, separable, nuclear, Z stable, C-star algebra satisfying the UCT. It's fine. There's a nice class. This invariant, I also won't require spending a lot of time on it. Point is, it includes K-theory, including K0 and K1, and then it includes a space of traces, so some linear functionals over the C-star algebras that preserve the unit. And then the U just says I keep track of where the unit gets sent. And then there's some pairing map that tells you how the traces behave on projections. Okay, great. So I want to say now kind of our theorem. And I should have said this at the beginning. This is joint work with Michal Shaknievich and Mira, who gave the pre-seminar. Okay. And our theorem is, you can get this. So there are functions, theta prime, and this is on a set of all countable ordinals to themselves, such that KTU of A being theta of alpha equivalent to KTU of B implies A is alpha equivalent to B, and the converse too. Possibly a different function, but we don't have to take stabilization. Okay, and this is for all, okay, for all classifiable C-star algebras.
And so this.
Sorry, this quantifier should go here. The functions are
I was going to
independent.
say,
Yeah,
the
the
functions
functions are independent of the choice of the C-star algebras.
Yes,
yeah,
thank you.
Thank you. Okay, so we answer both of these questions. You can do it for all the rest of C-star algebras at the cost of not knowing what the actual function is. And the converse works. We get both. Yay. Okay, but I do think that the interesting thing here is not necessarily the theorem itself, but the proof strategy. Before I move on, is it kind of clear? I guess I want to make a very quick remark, and then I'll ask if there are any questions at this stage in time. So this quick remark is something that I've said verbally, but I think it deserves a little bit more. Mira made this point about successor ordinals, right? Somehow winning some game at the level alpha plus 1 is the same as saying for every element in A, there exists a corresponding element in B, so that A0 is alpha equivalent to B, B0. And then, okay, the same if you swap them. Okay, and I just wanted to emphasize here that this is literally saying at, well, let's say alpha is actually a finite n. This is literally saying I've built a map that sends n elements in A to n elements of B and looks like it is an isomorphism on the substructures generated by those tuples. And I'm extending to the very next object. Regardless of which thing you pick in the other structure, I have a way of extending. So the theorem like this is really saying at some level of similarity of KTU, I can construct, or I can always extend some partial isomorphism between A and B to the next level. Okay, questions before I start to fall off the deep end and say some things about the proof?
So can you just extend Elliott invariant, or is it something?
KTU is yeah, it's the Elliott invariant. That's fine. Mm-hmm. Yeah, technically I don't remember the ordering on K-theory, but it's encoded by where the unit gets sent, so it's okay. Yeah. Other questions? All right. So I want to say a little bit about how we prove this, because it's not by stepping through a bunch of C-star algebraic arguments. So things will start to get a little bit hairy. So this is probably the stage at which, if you don't want me to lose you, you'll have to interrupt me. It's likely. The way that we prove this is by using some descriptive set theory. Yeah. Let's talk. So I'm going to give this black box theorem. So there's this abstract, I'll call it abstract descriptive set theoretic classification theorem. We prove this. The proof is not that hard, but I won't talk about it because it's a very logic-heavy proof. Yeah. All right, so on the way to proving this, where does this come from? We actually prove a very general thing. So assume the following. You have two analytic subsets in some standard Borel space. Okay, you have some analytic map between them. I promise this will be visible in a second, sorry. And then you have analytic equivalence relations. Probably it's been a long time since you heard the word analytic in the way that I'm using it. All I mean is that I am the image of a Borel set under a Borel map. So it's like, I'm not quite Borel, but like I'm really close to being, yeah. All right, so slightly more complicated than Borel is how you should think of this.
So what's an analytic map then?
It sends analytic sets to analytic sets.
In the product, it's analytic set, or?
In the yeah, that's a fine definition as well, yeah. Yeah, the graph is analytic, this kind of thing. Okay, suppose also, so you assume all of this, and you also assume that whenever these two things are isomorphic, then this analytic equivalence relation is satisfied. Okay, what's the conclusion? There exists some finite, okay, not finite, there exists some countable ordinal alpha such that this already happens once I'm alpha equivalent. Okay, let me put this up so that people can actually see it. All right, so I have two analytic sets. This is a super, super general theorem. Two analytic sets, an analytic map, two analytic equivalence relations. I didn't do the second half with the F. All right, same for f, you know. If x isomorphic x prime implies kx f k x prime, then exists beta. All right, same thing. So that's just taking care of my converse, basically. Forget about this just for a second. The proof will be the same. You'll just like swap the things around, basically. The point is, if isomorphism determines whatever this analytic equivalence relation is, then in fact, there's just some smaller stage. I didn't have to go all the way up to isomorphism. This kind of makes sense if you think about it in terms of Scott's isomorphism theorem. The difference here is that in that Scott isomorphism theorem, it says you hand me a structure, and then I can hand you a sentence or some level alpha so that I determine the isomorphism class of that structure. But here it's just like I have an entire large class of structures, maybe. That's what this will end up being. And I can determine whatever equivalence relation, whatever sufficiently nice equivalence relation I care about using some finite stage. It doesn't depend on what x and x prime are, basically. Okay. I'm going to want to apply this. So there will be some applied version. X is going to be the set of classifiable C-star algebras. Y will be the space of all invariants, all these KTUs. K will be KTU as a map from X to Y. Okay, and then forget about the converse, the thing is the same. I'm going to choose E, the analytic equivalence relation is equivalence up to some alpha, right? Okay. So in that case, what do I have? Let's hope one of these talks works. We'll find out. In that case, this is automatic from the C-star algebraic classification theorem. If KTUs are isomorphic, then, well, the C-star algebras are isomorphic, so certainly they're alpha equivalent. This thing is just true in general. If I can write a nice logic down the way that I've done for C-star algebras, then this alpha equivalence will be an analytic equivalence relation on the class of all such structures. So we prove that in general. It doesn't require anything about C-star algebras. All right, and then the first two things are kind of the hard things. So maybe I'll mark this one. So star basically follows from a theorem, so some work of Farage, Hornquist, Toms. The title of the paper is actually the descriptive set theory of some invariants of C-star algebras. Very, very clear. All right, anyway, so you can kind of get that the Elliott invariant as a map is nice and Borel. Okay, modulo a little bit of work because really everything that we did fell over here. And once you start thinking about this problem, it gets a little hairy. I have to encode separable C-star algebras into a Borel space first. And then I have to worry about all of the adjectives that I did not name for the class of classifiable C-star algebras. So the first bit, well, it was strange to me the first time I saw it, but I've been told that it's actually fairly standard. You can encode separable C-star algebras in a standard Borel space by just saying, like, oh, okay, you have B of H. There's only one B of H. There's only one H, basically, you know, in the separable setting. So you have one B of H, and then every separable C-star algebra is encoded by some countable dense sequence of it, represented on the only B of H that exists. And so you just take the set of all sequences in B of H and encode that with its usual Borel structure, and this gives you an encoding for separable C-star algebras. Good. Okay. Right. And then, so I guess I'll go, last thing I'll say here, star is almost done by the same thing, the same work. It did a lot of work for us, except for the UCT. All right, so there were some adjectives I didn't name. You can take a look at some of these older works and do this Borel encoding, and you can discover that they are analytic requirements on this space of separable C-star algebras, and the only thing you have to worry about is the UCT. The only thing you have to worry about is the UCT. Sorry?
B of H is not separable, right? So it's not obviously it's not the Borel space. So
No, I'm saying, so the encoding is, so A is identified, A as C-star algebra is identified with some sequence AN in B of H, the natural numbers. You encode this with the topology coming from weak star convergence. So R is a standard Borel space. And yeah, okay. Okay. I mean, what actually happens is we have several encodings, and then we have to prove that they're Borel equivalent, like there are Borel maps between them, but this is the most approachable encoding anyway. You can also choose to encode them using this picture coming from logic. Yeah, there's a number of ways to do this, but. Okay, so now I only have to worry about the UCT. If you're familiar with C-star algebraic classification, the UCT is kind of a notorious condition. Because, well, it's a subject of, it's a major open problem whether every amenable C-star algebra satisfies this condition. So I don't actually know off the top of my head what the definition of what the UCT is, but I'll give a definition here. So a C-star algebra A satisfies the UCT if and only if. All right, it's going to be a nested definition. A is KK equivalent to a commutative C-star algebra. Thanks for the giggles. All right. Okay, so I've told you a definition, and it hasn't been enlightening at all. So pseudo definition, KK is, this is probably not the picture that the C-star algebraists prefer, but it's the one that will be useful for me. So KK is a universal functor from this category of separable C-star algebras to some abelian category. Additive category, maybe is the better term. Additive category. So a category that has a notion of addition on its morphisms, satisfying three things. All right, it's not really that important what the three things are. It's split exactness, stable invariance, and homotopy invariance. It's okay if these words only kind of make a vague, vibey kind of sense. I'm not going to get into a bunch of technical detail about the proof of such things. The point is, I'm trying to investigate this kind of mysterious condition, which is importantly used throughout classification, but we don't know if we really need it. And it's characterized by some universal functorial picture with a very nice, like, kind of finite description, right? And I want to prove that such a thing is analytic. And then a lot of machinery actually had to go into doing this. So the machinery is going to involve making a Borel structure on the space of categories. We've already kind of talked about this. You only have to worry about the morphisms now. And then the way that this actually happens is we make, oh, I've erased it. I wrote down a language for C-star algebras earlier. We make a language to discuss functors over a category. So there's like this kind of, we're just getting more and more abstract. We've taken category theory and then we've put logic on top of it. And then once you do this you can get to this analyticity of the set of all classifiable C-star algebras. Okay, that was kind of a lot. Questions before I continue? Okay. Yeah, usually KK is, yeah, okay. So I should say something else. My picture here, so this is from, oh, I should say this is Nigel Higson's. It's not from me. All right, so from a work of Nigel Higson, you can show that. So this is a universal functor, and it takes, this additive category has C-star algebras as objects. So this guy is, I guess I should say condition 0, acts as identity on objects. So this functor is identity on objects, and then the thing that we normally think of as KK is just morphisms between A and B in this category. Yeah. So yeah, in my picture, KK takes a single C-star algebra, spits out that single C-star algebra, but changes the morphisms to KK maps. Okay, good. All right. The difficulty of this is normally I have to spend 15 minutes talking about games. And now I'm like, ooh, we're here, and I get to like say all the technical things, but nobody wants to hear that. All right, so we do two things. One is Borel categories of L structures. And this is general. Like you can do it for that relational language, which only has a less than symbol. You can do it for the language of C-star algebras, whatever you want. The point is I just need to enrich whatever the category is with some Borel structure, and it's going to be very, very close to the thing that we discussed earlier. So one is that you enumerate countable dense subsequence. Inside of your structure. And then you do the obvious identification of A with the ordinal omega, where you just take AI maps to I. Great. So this structure A, let's pretend it's a C-star algebra instead of the general case. So A has some distance metric given by the norm, meaning distance xy is norm of x minus y. So you can encode this distance as a map from omega squared to r. So omega squared is saying that I take 2 of these elements from my countable dense subsequence, and then I just compute. So you take some AI, AJ, something like this. Well, I guess here it's just IJ. You map it to norm AI minus AJ. Okay. And once you do this with something like the distance, you can also do it for everything else, right? So do the same for stuff like plus, times, adjoint, whatever, right? So every symbol you've ever cared about can just be encoded as some function on powers of omega back to either omega or r, whatever. And it's really just capturing what happens to this countable dense subset, but by continuity you can recover everything about the original C-star algebra. Great. So this actually gives you a Borel encoding. So earlier there was this question about like maybe the B of H picture is confusing. In that case, the Borel structure is really coming from like A is identified with omega. Then there's this distance which looks like a function from omega squared to r. And then like, okay, the same thing happens with plus. And then whatever. This terminates after some finite number of things. And you write down some big gross product, but the point is that each of the things in the gross product have a standard Borel structure, and then their product does as well. Okay, so this gives you an alternative encoding of separable C-star algebras in a nice Borel way, and then you have to do morphisms. So you have to do a bit of work to encode morphisms. And kind of the idea here is that you use some Cauchy sequences of fn's of your AJs. Maybe I'll say it like this for A and A naught. So a morphism on the entire algebra will be encoded by at least one such Cauchy sequence, and then you have to actually do a little bit of quotienting work so that you don't get duplicate copies of sequences, but fine. It's, everything has to be done in a countable way, and you have to do a bit of bookkeeping, but it's not that insane to make a category with Borel structure for C-star algebras. And really, I didn't need anything about C-star algebras to do this either. It generally works for any language.
So speaking about duplication, like
yeah.
You're identifying C-star algebra with some arbitrary candle lengths, some subsequence. But I imagine the sequence, you might be able to choose different sequences which still go to the same value.
Yeah. That's definitely true. Yes.
Okay. But you can quote this out and it's all Borel.
Yeah, that's okay too. Yeah, so lots of stuff is happening under the hood, but the idea of how the encoding works is definitely just to do this. Great. And then we got to talk about KK. So, all right, great. Now I have this Borel category for C-star algebras. And the only thing left to do is try to get, okay, something is a universal functor over this Borel category satisfying some conditions. I need to say that this condition is analytic in terms of this Borel structure. And the way that one does this is you build a logic over this, and then you write down what it means to be homotopy invariant or split exact in terms of these sentences. So earlier I gave a very simple example, like a C-star algebra is commutative if and only if. Here's this sentence. You can do the same thing for all of these with some countable family of sentences, and then you can determine that that thing is analytic. But okay, the real ingredient is we make a language for functors. And I think that this, too, the idea is not insane. So earlier I said, if I asked you what the language for C-star algebras is supposed to be, you would tell me that you need a 0, and you need a 1, and you need a plus, and you need a times, and so on. And I forgot about scalar multiplication. Fine. Okay. This is like a natural set of things you would need to talk about C-star algebras. If I turn around and ask you, what do you need to talk about functors? Something with composition, something to say composition is associative, etc. Maybe I also want a few other things. But okay, so if I wanted a language for functors, one thing is I need to keep track of source and target spaces for morphisms. So, over a category C. Okay, for all x, y, which are objects in this category, include, okay, I'm going to use this word which looks scary but shouldn't be, I include a sort morphisms of x, y. So this is a formal thing from logic which just says, okay, I'm doing some bookkeeping telling you that I live in a certain space. So I have a space for all morphisms between x and y, which somehow implicitly remembers which object I came from and which one I go to. All right, and then for all triples of objects, you have some symbol which is meant to be composition, Cx, y, z. And so this starts, okay, in morphisms from x, y cross morphisms y, z, and then ends up in morphisms from x to z. All right, so the symbol will be interpreted as composition, just like the symbol that I put for plus will actually be interpreted as some addition of algebra elements. And then, just for the sake of ease of writing such things, I include a symbol for all my morphisms as well. So for each, I don't think this is strictly necessary as a side tangent, but it makes my life easier to do it, so I'll do it. A symbol. So if I have some morphism, I include a symbol for it, and it lives in the correct space, the morphisms from the source of f to the target space. Okay, and then you just include some reasonable axioms. So axioms, associativity of composition. That composition actually is, that this symbol for composition actually is what it should be. So Cx, y, z of some f and some g should be honest to God, f composed with g. All right, and that the symbol for the identity on an element is identity. Okay, so you kind of do the obvious things, the things that you would do if you thought about logic and wanted to make a language for functors. And the shocking thing is that you do this encoding of morphisms, and then you work really hard for a couple of pages to show that these three things are actually analytic conditions. And then you're really, really happy. So I think what's happening is you kind of do the natural thing in each instance. For example, this I don't think has existed. At least I can't find it in the literature. This probably has existed, but I don't know of good uses for it. And what are you able to say? You're able to say, in fact, that the UCT is an analytic condition. So maybe I'll write this as like a little mini theorem. UCT is an analytic condition. And this points at something else kind of interesting just from a philosophical standpoint for classification of C-star algebras, which is all the other assumptions in classification, unital, simple, separable, nuclear, Z-stable. These are all known to be Borel by this previous work of Farah, Tornquist, and Tobbs. And if, for example, so this is like huge reach, I have no idea how to do it, but I'll advertise it anyway. If you could show that nuclear intersect with UCT is strictly analytic, meaning analytic and not Borel, then you would be solving the UCT problem, right? Because nuclear by itself as a class is Borel, and its complexity would be different once you intersected it with this condition. So this says something about how complex this assumption is, and the answer is more complex than the other things in classification. Unsurprising. Great. No, it's not. I did not include the word strict here. Yeah, so I guess one open question is UCT strictly analytic? We don't show this. We got very hopeful and thought that we had a thing which proved this, but we realized that we greatly misunderstood how AF algebras work. So this is still open. And then the big reach question, which I don't think I see no feasible way of doing this anytime soon, is the class of nuclear and UCT strictly analytic. So you'll know that this is analytic because UCT is analytic and so is, and nuclear is Borel. So this intersection will be analytic, but the key thing is you have to show that it's not Borel in order to say anything nice about the UCT problem. But I really like this project because somehow it combines a ton of interesting, seemingly disparate topics, ends up with a nice classification theorem for C-star algebras in terms of this game theory picture, and then just like grazes a big open problem. And I don't know how to make any progress over here, but I'll advertise this anyway. Yeah, that's all I've got time for. Thanks.
Right. Questions for Jenny?
Yeah, I have a couple questions. So the first one, so this last theorem, you said UCT being analytic. Mm-hmm. So this is the formulation of the UCT that you actually use in the proof, that KK equivalent to a
Yeah. I have to use this universal functor picture. We tried to do it concretely at first, using Kuntz's picture with this like Q of A and then the universal free products. And most of the encodings work out. Showing that the Kasparov product is nice is incredibly difficult. I think it's true. I think it's true that the Kasparov product will be analytic, and then you can show it using some concrete, not universal functor picture of KK. And we tried that for a little while, and then we ended up coming to this instead. Yeah.
Oh, okay, cool. My other question is, do you think you can do something similar, not for classification of the C-star algebras, the objects, but for embeddings, using the extended invariant, the KTU with the...
I don't know enough about this program to comment.
Okay.
Yeah, so there's a question from the online audience asking how fast growing these theta functions are.
Yeah, so a sad thing about, I was very happy that this approach got me to avoid repeating a bunch of C-star algebra classification over 40 years or something. But a sad thing about this very abstract approach is I can't really say anything about theta. I don't know how fast it grows. I don't know if it's like omega times something. And the approach itself, because it relies on this abstract descriptive set theoretic theorem, like there's nothing, it's not even like, oh, I could dig into it and find out. It's, you would have to do something much more concrete to know. Yeah.
Right. Other questions?
I noticed when you were introducing the logic for C-star algebras, yeah, you just had one sort and you just had the norm as a function. But I thought in the original ones they had like a different sort for every n ball, and then they had like...
So everything has to be bounded. I actually do have a bunch of sorts for every n ball, and then you have to like include. So like the plus is really not a single plus. It's like a plus related to the two balls that you're working in, and then. But if I started saying all this stuff, people would be like, "Why would you do this?"
I would have given the talk the same way. But I was just wondering if you had a different way of doing things. But like,
no. It's the same. There are a bunch of sorts for the n balls. That's true.
Cool.
Yeah.
Any other questions? If not, then let us thank Jenny again.